Hey guys, so we have set ourselves with a wonderful problem and we have been trying to answer or come up with a solution for it. So we want to find basically who damaged our bike. So as cool as it might sound, unfortunately that was not the problem that we set up. The problem is we have a bike that has been permanently damaged, a part of the bike, the rim that has been permanently damaged, and we want to rather describe this permanent damage inflicted on the bike using a mathematical expression. Now, the cause for this damage is the force that has been imposed on that crystalline system, and because of the force there has been, in response to the force, there has been a dislocation, the movement of atoms from its original position. The positions of the atoms have changed now. Now, based on this understanding, we have come up with an expression like that, which describes the force that dislocates your atom. And when we solve this expression here, you end up having a solution that gives us the position of the atoms at a given time t. Now, when we know the change or when we know the position of the atom in response to the force that you have imposed, what you end up having is you will be able to relate this change in the position of the atom to that of the permanent damage that you see on the cycle. So that is what the problem that we have posed ourselves, and we are trying to come up with a solution for this expression here. For this expression here that describes the cause of our problem, that describes our problem in its entirety. The solution of this will help us describe the position, and this position can be translated to the overall permanent damage that we see in our system. Now, we don't want to just solve this problem and come up with a solution. Our goal is rather to build a tool that will help us solve not only this problem, but any problem that has this particular setup, that has this form here. So basically, as far as this problem goes, you have a second order ordinary function or differential equation, a second order ODE. Now we want to have a tool that will help us solve such similar higher order ODEs, not just first order ODE, but similar higher order ODEs. So that is our goal. We want to not to just solve this problem, we want to come up with a tool that will help us approach such problems. Now, in order to build that tool, we make a primary assumption that states that the solution of such an higher order ODEs is smooth and continuous. We make that assumption that the solution that we intend to find out is rather smooth. So what we mean by smooth is, we mean that the solution is differentiable. We are able to differentiate the solution. We are able to differentiate the solution once, twice, so on and so forth at a given point. So that is an assumption that we make, and we refer to that as a smooth function. So when we make that assumption, when we give that assumption, it is possible for us to write the solution f of x as something like this. It is possible for us to write the solution that is smooth, that is differentiable, in this form like this. We refer to this as a power series. Now, the f of x here is a generalized solution for something of this sort. So when I have an expression instead of what we have mentioned, the specific one here, it is written here, when I have a similar expression in a generalized case, it will be something like this. A double derivative of f of x will be equal to k by m. I'm just bringing my m from here to here, and f of x. The solution for this, a generalized way of representing my expression here in terms of my expression here, when I'm expressing it in a generalized way, I end up having something like this, and a solution for this expression will be my f of x. And when I assume my f of x is continuous, I will be able to write my f of x in this form, which is referred to as the power series expansion. Now I have a power series expansion in terms of my x, that is variable, and if I'm able to find out these coefficients a0, a1, a2, a3 and so on and so forth, if I'm able to find out these coefficients based on my original relation here, then I will have an f of x that will satisfy my expression. Again, I assume my solution to be continuous, and the continuous expansion of my solution comprises of two terms or two categories of term. One is my variable, another is the coefficient. If I'm able to ascertain the coefficient based on the original problem that I have set up, then this f of x will turn into my solution. Now, when you focus on these coefficients here, these coefficients are nothing but the derivative of my function f of x at a given point. These coefficients are nothing but, this is something we saw in our previous session, these coefficients are nothing but the derivative of my solution at a given point. If the given point is any random point, say capital B, then the expansion turns it to something like this. My expansion will turn to something like this, meaning now instead of having some unknown coefficient, I have the coefficients being replaced by the derivative of my function at a point B. So I no longer have any unknown coefficients like a0, a1 and so on and so forth, but rather I have my function at B, the first derivative of my function at the same point B, the second derivative of the function at same point B, the third derivative of my function at the same point B, and so on and so forth. When I know the derivative of my function at a given point, I will be able to come up with the expanded version of my solution. So it's no longer unknown, it's just the derivative of it. Now instead, at a random point B, if I'm able to find if my solution is differentiable at a point 0, at the point of origin 0, then instead of B, I can replace my B with 0. I end up having an expression like this. So I assume my function to be, my solution to be continuous, and that assumption has given me unknown coefficients. Now these unknown coefficients turns out to be the differentiable or differentiated functions at a specific point, and when I know the first derivative, second derivative and so on and so forth at the specific point of my function, then I will be able to have the expansion of my solution, and these expansions are called as Taylor series expansion. In this case, you have a generalized Taylor series expansion at any random point B, and here you have the Taylor series expansion at the point 0. So it is possible basically to find out your a0, a1 and a2, those coefficients, by considering the derivative of the functions. And when your function is differentiable, it is possible for you to have non-zeros values that will replace these coefficients. Then essentially you have an expanded version of your function that is a solution. That point wherein your function is differentiable can be B or it can be 0, and depending on it, the expanded series, the power series, turns into either this form of Taylor series or this form of Taylor series. Alright, we assume the solution, we have unknown coefficients. Now these unknown coefficients turn out to be the differentiation of your function at certain point. Now before using this understanding to a solution, we will try to gain a bit more, we will try to dig a bit more into what these coefficients mean. So what these coefficients mean. When I say that these are differentiable at point 0, how will they turn out to be? So this is something we will spend few minutes on before getting into the solution, so as to get a feel for how Taylor series generally works. So whenever it is possible that you have gone through some physics problems, or you have been reading through some physics problems, and towards the end, when you see the solution, you find the solution as weird sin x and cos x in it. Of course, we are no longer introducing any trigonometry, we are not introducing any right angle triangle, but the solution somehow seems to have some sin x and cos x to it. Now what essentially we will try to understand is, from where does the sin x and cos x come into play? When we are not talking about in the context of any right angle triangles, when nowhere the geometry of the problem that we are discussing is involved, but still we find sin x and cos x getting introduced in a real life problem that we are discussing. So what we are about to see will be able to give a solution for that so-called mystery. You are seeing a physics problem, it has all this algebraic expression there, but finally the solution comes out to be in sin x and cos x. Why and how it happens? This is something that we will try to answer. Now, we have a Taylor series here, and this Taylor series expansion is for a function, and let us assume that this function is sin of x. Now what I basically want to do is, I know my sin of x is a continuous function. It is one of the smooth functions that I could think of. So it means it is possible for me to consider its derivative at a given point 0. Now let us try to do that. If I substitute, if I want to find my f of 0, if I want to expand my f of x, that is sin x, into this Taylor series, I need to have terms for, or I need to have something to substitute for each of these terms here. So if I consider the first term and substitute my x as 0, this term will turn out to be 0. There will not be any non-zero term for this here. And now I take the derivative of it, I end up with cos x, and when I have cos x and substitute my x equal to 0, my term turns to 1. Now take the second derivative of it, it becomes minus sine x, and when I substitute my x as 0, it becomes 0. I take the third derivative of it, I end up having minus cos x, and substitute my x as 0, this will turn to minus 1. So I take my sine x, in the case of the first term, I just substitute my x as 0, I end up with one value. I take the first derivative of it, substitute my x as 0, I come up with another value. I take the second derivative of it, substitute my x as 0, get a third value. Third derivative of it, substitute my x with 0, I end up another value. So when I replace all these derivative terms with the zeros and ones that I've got, I end up having an expression like this, and this using the summation function can be expressed like this. So basically, when I have a smooth function like sine of x, it is possible for me to write the sine of x in this form. And now, when I'm solving a physical problem and the solution of the problem adapts a form like this, then I can replace the series here with sine of x. So basically, this sets up a foundation wherein a function, when it's smooth, can be described based on its derivative. And when you see a derivative based an expression in the form of a series, it is possible for us to go back to the function. So that's the reason why when you are dealing with a physical problem and you end up having a series like this, we can replace this series with sine x. So you are dealing with, say, some sort of an oscillatory motion of a spring, and when you solve this oscillatory motion of a spring, you end up with a series like this, and this series now can be replaced with sine x. Now it's not only restricted for sine x, we have the other smooth function that we know of as cos x, and we can take the same approach that we took for sine x. We can, for this term, we can substitute our x equal to 0, you end up having the first term to be equal to 1. You take the derivative, you get sine x, and substitute x equal to 0, it goes and vanishes off to 0. Now we can take the derivative, the second derivative, third derivative, and so on and so forth. You will end up having an expression like this. Now, when you're solving a problem, you end up having an expression like this. So basically what it means is this series here can now be replaced with cos x, and this can be represented in the summation form using this notations here. So basically, you take a physical problem, you try to solve it, and the solution gives you a series like this. It means the series can be tracked back to your sine x and cos x. So it's not that you start off with the f of x, because f of x is generally not known to us, but when you're solving a problem, you end up with a series, then it can be simplified as sine x and cos x. Now, since this has been dealt with in this session, you guys can try for e power x. You can take our function as e power x and try to solve or try to get an expanded form of the e power x. If you try to do so, it's pretty straightforward, because e power x, when you take the first derivative and second derivative and so on and so forth, stays e power x, and when you substitute x equal to 0, you end up having 1. So all you will be doing is substituting your coefficients with 1. So basically what you will end up having is an expression something of this sort, which can be summarized as this. So this series will represent your e power x function. Now, what these series essentially mean is the function that you have when you consider each of these functions and each of these series, and both of these mean when they are equivalent to one another, what it essentially means is this function here on the top, let's say your RHS, or RHS is rather can be approximated by these series of terms here. So when we say that a given function is equivalent to a series of terms, what we basically are saying is this function can be approximated by series of terms. Why not? Even though we are equating it, why we call this as approximation is because there is something that we cannot accurately capture, and that something is captured, or that something is indicated by these dots here. The reason we call these expansions as approximation, not the accurate solution, not the exact solution, but approximations, is because very rarely we capture all the dots. There are still dots, higher order terms that are involved. The reason these higher order terms are important is something that you yourself can understand. To understand that why these higher order terms are important, because of these dots, we call these as approximation, not the exact solution. You can understand it by plotting your function geometrically. You can take any tool and you can plot your original function e power x. Let's say this is being the simplest function. We can plot our e power x, and this will give us a curve like this. So this is our original solution, e power x. Now, we will try to plot in this coordinate system. In this plot, we will try to introduce a line or a curve that just considers the first two terms, 1 plus x. So we want to superimpose a plot, a line that includes 1 plus x, and when you do that, you end up having a line something like this. So you have your original function and you just take the first two terms and you superimpose on it, you get a line like this. So of course these two are not equal at same point. These two do not overlap at same point. They are not equivalent at all points, at least in some initial regions. Of course there might be some overlap, but as you move along the x, you see there is a significant amount of deviation. Now one other thing you could do is, in addition to the first two terms, you can include the third term. And when you include the third term, you would observe that when you plot it, you would observe that the third term makes the approximation, the series, much closer to your function. In the first, when you consider first two terms, there is a significant amount of deviation. When you introduce the third term, there is your series now begins to get closer to your original function. Now when you include your fourth term, you see that the series becomes even more closer. So basically what it means is, the more terms you had in the approximation, the more closer your approximation gets to the original solution. Now when you add your fifth term, the fifth term will be even more closer. So this you can actually verify by plotting it. You can take your Maclaurin or any other tool you can use, even your Google, just you can plot e power x, and then you can plot 1 plus x plus x squared by 2, 1 plus x squared by 2 plus x cubed by 3 factorial. You can keep on doing that, and you would see every time you introduce a new term, your curve gets closer to your original function. So it means the more terms I have in my solution, more accurate my solution is going to be. My more terms I have in my solution, more accurate my approximation is going to be. More accurate my series representation of my original function is going to be. That is what this plot here shows. The more terms I have, the more accurate my series expansion of my solution is going to be. The only way possible for me to have more of these terms is when my solution is differentiable at higher orders. If my solution is not differentiable at higher orders, these terms will turn to 0 automatically. But when my solutions are differentiable at higher orders, then I will be able to have non-zero terms for all this and more to come. Then it becomes possible for me to come as close to as the original function using this series expansion here. And that is the reason we started off by saying that we assume our solution is smooth. And when we assume our solution is smooth, it means it is possible for us to differentiate the solution at higher orders. And when I am able to differentiate my solution at higher orders, I will be able to get an increased number of terms in this series. When there are increased number of terms in the series, I will be able to get closer to my original function. So the series will then be a more accurate representation or approximation of my original function, and all the solution that I get in the series form will be a more accurate representation of my original function. And that is the reason why we refer to this, or we assume that, or we on the very outset we say that the solution is, we assume it to be smooth. Smooth meaning we are able to differentiate at higher orders at a given point, and that will ensure that all these terms exist, and when these terms exist, then we are able to get closer to our original function. Now just before we wind up, these Taylor series expansion of the specific functions, the Taylor series expansion of sine x and cos x and similar specific functions, they are referred to as the Maclaurin series. So this is something, a vocabulary that you can add to your dictionary. So what we have seen in this session is, we have seen that the higher order derivatives, they indicate the smooth function. The more higher order derivatives you have, the smoother your function, and more accurate is this series, the Taylor series representation of your original function or your solution. Now when you are solving a physical problem and you end up with a series like this, it is possible for us to replace this series with sine x and cos x. So one critical point we need to understand is now we are going to solve a physical problem, and when the physical problem gives us this series, it is possible for us to get back to sin x and cos x, and ideally then our solution will be in terms of sin x and cos x. So with this understanding, now that we have understood what power series expansion is, now that we have understood what a Taylor series is, now that we have understood how sin x and cos x can be introduced in a physical problem, what renders such introduction, we will try to, with this, equipped with all these understanding, we will try to solve a problem that involves a second order ODE in the upcoming session. Goodbye.